On the other hand, negatively skewed curves have the long tail of the curve pointing to the lower end of the scale, with all of the scores bunched to the right of the center. So now we're going to talk about descriptive statistics. So first you're going to talk about measures of central tendency. So central tendency is a single number that represents a data set. For example, the mean, median and mode are examples of central tendencies within statistical distribution. Use of these central tendencies allows researchers to level out widely varying data points. The mean, median and mode are all really straightforward to calculate and are all really influential for representing data set as a collective. When calculating the mean, otherwise known as the average of a data set, you add all the data scores and then divide that sum by the numbers, by the set of numbers, by the count of numbers in the set. Secondly, the mode provides you with a value that occurs most frequently across a data set. And finally, the median is the middle value in a series of numbers. The mean, mode and median are common bits of data that are used when it comes to a researcher presenting their data findings. They are easy to calculate, but can say a lot about a data set. If we take the static sprint scores from the gymnast data, the mean of the scores is 2.72. The mode can't be calculated due to all the scores being different. And finally, the median is 2.315. I would say overall, the mean is the measure of central tendency that is looked at and used the most by researchers. On the flip side, measures of dispersion help to understand the variation in data. The common measures of dispersion include the range, standard deviation, and the interquartile range. Firstly, the range, like I've already explained before, is the numerical difference between the largest and the smallest value of a data set. Secondly, the interquartile range is a measure of where the, let's call it like the middle 50-50 is within a data set. The range gives us a measurement of how spread out the entirety of a data set is, whereas the interquartile range tells us how far apart the first and third quartile are, indicating how spread out the middle 50% of a data set is. Because the interquartile range is the middle 50%, it doesn't take into consideration any outliers, which is a positive, because usually any outliers within data can have a negative effect on a researcher's data analysis, often why they are ignored. The steps to finding the interquartile range are as followed. First of all, you need to put all of the values of the data set in order. As you can see from my example on the screen, I used the biceps skin fold caliper data of 14 gymnasts. Once you put the data in order, you split the data into two by marking the middle of the data. You then need to find the lower quartile and upper quartile from the split data. The lower quartile is the median of the lower half of the split data, and the upper quartile is the median of the upper half. As you can see, the upper quartile and lower quartile of my example are 5 and 10. Finally, to calculate the interquartile range, you very simply subtract the lower quartile from the upper quartile. In my example, the interquartile range was an easy whole number, but it can be a decimal. The final measure of dispersion is standard deviation. Standard deviation is a measure of how spread out a data set is. A low standard deviation tells you that the data is closely clustered around the mean, whereas on the flip side, a high standard deviation indicates that the data is dispersed over a wider range of values. It is used only when the distribution of data is approximately normal, which is what creates the bell-shaped curve on a graph of normal distribution. Calculating the standard deviation of a data set can be broken down into 5 steps. Firstly, you need to calculate the mean of the data set. Then you subtract the mean from each bit of data to find the differences. Thirdly, you have to square each difference each difference to make a difference, to make all the differences positive, so that they don't cancel each other out. After that, you calculate the mean of the squared differences, and then finally you square root the mean value of the squared differences divided by n minus 1. As you can see on my screen, I worked out the standard deviation of the triceps skinfold calipers from using the standard deviation equation, which turned out to be 2.93 millimeters. So now I'm going to move on to part 4, which is inferential statistics. So one of the most effective ways of deciding what statistical test is best for you and your study when testing for a relationship is by using a decision tree. Adam et al. Describes using a decision tree like planning a train journey, because if you follow the lines you will end up at your destination. On the screen is an example of a decision tree that a researcher could use that they would follow depending on the type of data they've collected. There are 3 types of data: nominal, ordinal and interval or ratio data. Depending on the data a researcher collects can influence the statistical test that they use. For example, if I collected interval or ratio data, I would follow the interval or ratio line coming off the type of data. I then come to my first cross, where I'm deciding whether I'm looking at a relationship with my data or analyse the mean difference. Let's say I'm looking to analyse the mean difference of my data from pre and post consumption of Powerade on footballers' agility. Because of this, I'd follow the line down to the next cross, where my data is either 2 separate groups or 2 related groups. My example is 2 related groups of the data, because it's pre and post scores of only one group of participants. Therefore, I'll be using a dependent t-test for my statistical analysis of my data. That is obviously just one example scenario, but the same idea applies for all of the other routes, depending on the type of data that you've collected and what you're trying to compare. Along with talking about decision trees, I'm just going to briefly run through the differences between an independent and a dependent test. As you can see on the exemplar decision tree, it already gives a hint as to the major difference between the two, and that is that an independent test examines the significance of the mean scores of 2 separate groups, whereas the dependent t-test examines the significant difference between 2 sets of related data. An example of when you could use the dependent t-test to examine significance could be pre and post scores of a long jump after a 6-week training program. In addition to this, I'm going to compare parametric and non-parametric testing. So a parametric test is described by Adams et al. As a statistical test that uses interval or ratio data that has been drawn from a normal distribution with the same variance, whereas a non-parametric test is simply a statistical test that uses ordinal or nominal data. Examples of parametric tests are t-tests, ANOVA, MANOVA, and Pearson's product moment correlation coefficient. On the flip side, examples of non-parametric tests are the Mann-Whitney, Spearman rank order correlation, chi-squared, and Wilcoxon matched pairs signed ranks test. It is important to note that all of these tests for statistical significance relate to the null hypothesis of a study. So I'm just going to run through examples of a parametric test, a non-parametric test, and then the parametric test for independent t-test and dependent t-test. So first of all, Pearson's test is a parametric test that is suitable when you're trying to find a relationship between 2 variables, having gathered interval or ratio data. Due to it being a test of association, it aims to look at whether 2 or more variables are related. The 3 stages used in this parametric test are firstly summing up each of the scores, secondly squaring and then summing each scores, and then finally multiplying each pair of scores and obtaining the cumulative sum of these products. You then put the values created in the first steps into the relevant places in the formula, which is what provides your R value. Presented on my screen is the steps I took for using the Pearson's rank order correlation coefficient test on the data for bicep and tricep skin fold calipers of 8 gymnasts. Once I have my R value, I have to interpret whether the R value is significant or not. This is done by firstly selecting my level of significance, which is 0.05. In addition to this, I need to select my degree of freedom, which for this test is n-2. A degree of freedom is used as a correction factor to limit bias and the effect of outliers. To conclude, if the results is equal to or greater than the critical value, which can be found in the table, the result is seen as significant. In my example, my calculated value was smaller than the critical value, and therefore there is not a significant relationship or correlation between the bicep and tricep skin fold calipers. On the flip side then, an example of a non-parametric test is Spearman's rank order correlation test. This test is similar to Pearson's correlation coefficient due to its purpose. However, it is a non-parametric equivalent, and it is used when the data has been ranked, otherwise known as ordinal data. Ideally, this test should be used when you want to find a relationship between two sets of ordinal data. For example, golf driving distance and final leaderboard position. The example I used, that is presented on my screen, is the relationship between systolic and diastolic pressure when resting. The first step is to rank the data being used. As you can see on my screen, the table at the top of the screen, I ranked the resting systolic and diastolic blood pressure of 10 gymnasts from highest to lowest in the third and fifth columns. Following this, you determine the difference between the data, and this must be squared and then added together. You then put the values created in the table in the relevant places in the formula, which is what produces your R value. My steps of doing this are shown and broken down on the bottom left image of the screen. Finally, just like Pearson's tests, you need to interpret the significance of the R value. The level of significance I chose was 0.05, with a degree of freedom being n-2. I compared my values to the table of significance to be able to find out whether my results were significant or not. As you can see in the bottom right image, my calculated value was smaller than the critical value, which means there is no significant relationship or correlation between systolic and diastolic resting blood pressure. Thirdly, my example of a parametric independent t-test is looking at significance between standing vertical jump scores of a male and female gymnast. An independent t-test is used when you have two groups and are trying to discover if the mean scores of the two groups can be considered to be significantly different. Therefore, in my example, I am doing a dependent t-test to test if the mean scores of the male standing vertical jump and the female vertical standing jump are statistically significant or not. It is also important to note that the independent t-test is suitable when the data you have collected is interval or ordinal data. In my example, it is interval data. The first two steps of my example were to calculate the mean and the standard deviation of both the male and female scores, which is presented in the table at the top of my screen. After that, I put these values in the relevant place of the equation to give me a t-value of -0.7. The final step, as shown in the other two test example, is to work out the critical value by using the degree of freedom, which is n1 plus n2 minus 2. With a value of significance as 0.05. If the calculated value is higher than the critical value, then there is a significant difference. However, if the critical value is higher than the calculated value, then there is no significance. In my test example, to test to see if there is a significant difference between standing vertical jump scores of male and females, the critical value was way above the calculated value, and because of this there is no significant difference.